Good afternoon, everyone. Welcome to the Toronto Geometry Colloquium. This is a weekly series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we're going to have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving a keynote presentation.
Today, we're thrilled to have Keunhong Park as our opener to talk about topologically varying neural fields, and three members of the New York Times Research and Development team to talk about how technology can be used, hopefully for good, in journalism. If you have any questions for the speaker, you can write them either in our Discord channel, Discord server, or in the YouTube live chat that we'll be monitoring. And make sure to ask all your questions early and when you think of them so that we can curate the best Q&A experience for all of us. Our first speaker today is Keunhong Park, a PhD student at the University of Washington. He has a Samsung scholarship and has worked for everyone from NVIDIA to Google to Amazon, among others. He works on applying insights from both computer graphics and computer visions to challenges that fall at the intersection of both fields. And as someone who's currently working on a similar part of our area of research lately, I can very much appreciate how the world needs more people like Keunhong that work and are very successful in bridging the gap between graphics and vision. Today, he's going to tell us about topologically changing deformations and how to learn them. And by the way, he's in the job market. Let's give a warm welcome to Keunhong Park.
Hi, thanks for the great introduction. Can everyone hear me? Yes. Yep. So like Sylvia said, my name is Keunhong, and today I'm presenting HyperNeRF, our work on capturing dynamic topologically varying scenes. So our goal for this project is casual capture. Imagine you want to scan something just by waving your phone around it. For example, here I'm showing Alex, my lab mate, scanning himself by taking a selfie video. Now, to spoil the ending a bit, NeRFies, like our previous project, can take that video and turn it into a photorealistic 3D representation that you can render using whatever camera you want. So this project, NeRFies, builds on NeRF, or neural radiance fields. NeRF takes a loose collection of images and it turns them into these beautiful photorealistic 3D reconstructions. And kind of the main part of NeRF is that it stores the 3D scene in the weights of this fully connected neural network. And this network has 5 inputs, the spatial positions, XYZ, and 2 angles, which are the viewing directions that let it encode view-dependent things. And the output is just an RGB color and a density value. The way you render a NeRF is you take each input image. So you can imagine you have a bunch of observations, and you can imagine each image is sort of floating in space where it was taken. And if you shoot a ray through a pixel, it traverses the scene, and you can sample points along that ray. And for each point, you query the MLP. And what this does is it gives you a color and a density value for each point. And now you can traverse that ray while accumulating color and density. And this should give you an output color for that pixel of the image. And to train a NeRF, you just impose a loss on that, and it kind of optimizes the scene. So results from NeRF that, if you train it this way, are pretty much photoreal, and it can model thin structures like the leaves of the fern on the left, and it can kind of handle transparency like glass, like the glass of water on the right there. But sadly, we can't just use NeRF for our goal. If you run NeRF on our inputs, you'll get these kind of awful results with weird floating artifacts. And what's happening here is NeRF is overfitting to the training set without creating a coherent 3D scene. And the reason this happens is fairly straightforward. Say you have 2 images of a person. If you grab a point from each image and you see where they land, in this example, I'm showing the corner of Alex's glasses. If you shoot rays through these points, they won't land on the same spot because Alex is moving. And this causes issues because now we're trying to update the volume, but the images aren't consistent. And typically, NeRF will try to explain these by creating tons of tiny floating things in the air that explain each training image, but don't result in a coherent 3D scene. The fix for this is we're going to define a canonical template frame. And we're saying that there's only one Alex, and he's going to live in this one canonical frame. And all these images correspond to a deformed version of this canonical template. So instead of shooting rays through the volume, rays from each image bend to land on the right spot in the template. So to actually do this, we're going to introduce a second MLP, which also maps from input XYZ coordinates, but the output, instead of being the radiance, is a different XYZ coordinate, which lives in the canonical frame. And each training image is going to get its own latent code that conditions the deformation. So if you have 100 images, you have 100 latent codes. So when you train the network and the codes, the points get deformed and land on the canonical frame. So skipping a bunch of details for NERFs, taking this approach gets you pretty good results. We get all the details in the hair and the beard. And if you look at the depth map, you might notice we're also capturing the geometry of the hair as well. We can also capture non-human things like Toby, my girlfriend's dog. Unfortunately, this method has a major limitation. We can't handle changes in apparent topology. For example, if you take this video of Ricardo making a bunch of funny faces, the reconstruction ends up looking really bad. You can see the geometry is really buggy and it makes the output look unrealistic. And we call this the pelican bug for obvious reasons. It's pulling out his lips and making him look like a pelican. So why does this pelican bug happen? Let's consider an example where I'm opening and closing my mouth. If you remember from a couple slides ago, NERFs maps each point in the observation frame to a canonical template. A template with a closed mouth can't model what's inside the mouth, so it has to be open. So we're going to run with that assumption. But then what happens if we try to render a closed mouth? Two adjacent points that are just off by an infinitesimal amount need to be mapped to distant points on the template. And this means there needs to be a discontinuity at the seam. Unfortunately, we're modeling the deformation with an MLP, so it's necessarily continuous by definition. And that means we can't model these kinds of discontinuities where my mouth opens. So that's why we can't model topological changes. To explain how we're going to fix this problem, we have to take a little bit of a detour. Say you have these three shapes and you want to be able to morph between them. It's not immediately obvious what the best way to do that is. You could try dividing them up into points and move them around, but there are always some weird edge cases that are hard to deal with. So it turns out there's a really clever approach to these kinds of problems, and they're called level set methods. The only idea we're going to take from level set methods is this idea of modeling shapes as cross-sections of another higher dimensional shape. Here we're showing a 3D shape that we obtained by optimizing a signed distance field, or SDF, to contain these three 2D shapes. And if you slice through this 3D shape along the z-axis, you get our 2D shapes back as cross-sections. So we call this new axis the ambient dimension. And you can see in this case, it's the z-axis. But if you want to model 3D shapes, it would have to go into higher dimensions. And notice how natural this is. There's nothing complicated happening to morph between the shapes. All we're doing here is moving a plane up and down. So to apply this idea to NERFs, we just take our template NERF model and just add an extra ambient dimension to the model. Doing this gives us a space of templates. Here I'm showing an example with 2 ambient dimensions. So you can have more than one ambient dimension. Each point along the ambient dimensions corresponds to a different template that can represent different topological states. You can see the space here contains versions of me with my mouth closed, my mouth open, with teeth and without teeth. So adding these higher dimensions pretty much fixes the pelican bug. Here we're interpolating between several states in the input video. And you can see it fixes the largest errors. So it's rid of the pelican bug mostly, but the result is still far from perfect. The teeth are still a bit blurry and there's this weird fading artifact that happens during interpolation. So how can we improve this? Let's look at another example that exposes another issue. So I've changed the shapes around a bit this time, and there's an O and an X in different permutations. If you optimize the higher dimensional shape like we did before, you get something like this. And now let's try to interpolate between the red shape and the green shape. And you'll notice that the interpolation is a bit messy and it doesn't seem like a smooth transition. It kind of goes through this weird intermediate shape. And this happens because all you can do is move the plane up and down. So if you're going from the red shape to the green shape, you have to go through the yellow shape. That play one more time. So our solution to this is to let the slicing plane bend. So instead of just slicing straight through the shape, we can slice with these kind of bending deformable sheets. And by doing this, we can get a much more direct interpolation that doesn't need to go through the other shapes in between. And you can imagine you can fit a lot more in the template space because now your slicing plane can bend. So this deformable sheet is, of course, encoded by another MLP. And this MLP takes an input coordinate and spits out an ambient coordinate W, which is the z-axis in this case. This essentially just makes the ambient coordinate spatially varying. So you have a different point for each point. And in this case, you might ask what the positional encoding does. The positional encoding controls how smooth the deformable sheet is, so depending on how many frequencies you give it. So to apply this to NeRFs, instead of using the same ambient coordinate globally for all spatial positions, we first query a deformable sheet MLP to get the W value for each spatial position. And architecturally, that's pretty much it. And that's all there is to HyperNeRF. Once we do this, the fading artifacts are gone and the reconstruction quality is much better overall. For example, there's much more detail in the teeth. It's a lot sharper. And also the eyes. And that's how HyperNeRF works. Now I'll move on to showing some results comparing to the original method NeRFs. Here we're rendering the scene from novel views while playing back the video states. And you can see the pelican bug occurring around my mouth. And there's also kind of a lack of details where my eyes is a little bit blurry. And if you compare that with HyperNeRF, HyperNeRF manages to handle deformation much better. Here's the example I showed to introduce the bug. And you can see the same issue going around the mouth area. Geometry is buggy, and HyperNeRF works better. So HyperNeRF also improved results for scenes where two things make contact, because touching something can cause discontinuities as well. You can see weird artifacts happening when the hands kind of touch. While HyperNeRF, while not perfect, it does handle it much better. Here's a qualitative result where I'm splitting a cookie in half. And this is an example where I'm pulling an espresso shot. So it actually seems to handle kind of transient effects like the liquid and transparency quite well. And lastly, here's an example of my 3D printer. So this one's technically not a topological change, but like the print bed moving relative to the base, that can cause some issues with deformation sometimes. And that's all I have for you today. Thanks.
Thank you very much, Keunhong. That was an amazing talk. I'm fascinated by just how far the NeRF field has gone in what feels like a few months. Great job. Now we'll move on to our, if you could please stop sharing screen. Thank you. Now we'll move on to our headliners talk, and we'll have a joint Q&A for both at the end. Maybe we'll ask them if we could have newspaper bylines that are GIFs, you know? Why do we have to stare at the journalist's image? That feels like 20th century. Okay, so our headliners today are Justin Lewis, Nicholas Bartsakas, and Lydia Jessup from the New York Times Research and Development team. And I'm extremely honored that they're joining us today. You might be able to tell I'm very excited. One of my very first actions when I moved to North America was becoming a New York Times subscriber. I've always been impressed, not just by the quality of the journalism, which is a given, but also the will to try new things, even as such a big institution, and reinvent how journalism is done in the 21st century. From the Daily to the Visual Investigations team to embedding immersive 3D scenes in stories that you can navigate, to explainers and how it's possible to run 100 meters in 9 seconds, or how can a building collapse in a matter of minutes. I've always felt like there's a set of good, smart people behind the scenes working on pushing the boundaries of technology for the, I think, good cause of telling the truth to the public and holding those in power accountable. And I kind of assumed that group of people existed, but now I'm extremely honored to finally be meeting some of them, at least 3 of them. So Lydia Jessup, Justin Lewis, and Nicholas Bartzokas, you can take it away.
Thank you. And I think, Nick, you'll start presenting. Hi, everyone. Thanks so much for joining us. My name is Justin Lewis, and I head strategy for the R&D team at the New York Times. And I'm joined by a couple of my colleagues, and we'll do quick introductions of those to Lydia and Nick. And next slide, Nick, if you want to go to that. Lydia, do you want to do a quick introduction of yourself?
Yeah. Hi, everyone. And thank you so much, Sylvia, for that amazing introduction. I work as a designer on the research and development, or R&D team. And I'm primarily focused on the UI and the UX of our augmented reality projects, which you'll hear a lot more about shortly.
And hello, I'm Nick Bartzokas. Thank you very much, yes, also for that introduction and for pronouncing my last name right, which is amazing. I am a software engineer in the R&D department. I focus on data visualization and 3D graphics.
Cool. And so for the agenda today, I'm going to give a quick introduction of what R&D means at the New York Times and some of the principles of how we approach our work. Then Lydia and Nick are going to do most of the presenting today as they dive into one of the big areas of research for our team, which is spatial journalism. So they'll walk you through the entire process of how we bring spatial journalism to life. And then at the end, we'll share some other areas of research that R&D is working on, the types of research that we're interested in. And of course, be happy to take questions as well. Nick, you can go to the next slide. So what is R&D inside of a media company, and specifically the New York Times? What does that mean? Our mission as a team is to explore how to use emerging technologies in the service of journalism. And with the service of journalism piece, we sort of mean that in 2 ways. One is aiding our journalists and our company in reporting and news gathering more efficiently, more robustly, more accurately. And then on the other side of that is providing a news report to our readers that is getting faster, easier to use, more comprehensible, and more accessible. And to do that, we work closely with teams all around the company, from product and technology, but also the newsroom as well. And the skill set that we have within our team, represented a little bit here today, is, we have journalists within R&D, we have creative technologists, designers, engineers, strategists, a lot of different folks wearing different hats who come together to help push some of these emerging technologies forward. Next slide. Today, we're going to do a deep dive into spatial journalism. But before we do that, I wanted to give you a little insight into some of the other broad emerging technology interest areas that our team researches. We evaluate emerging trends in media and technology and try to forecast how those might play out over the next 2 to 3 years. And we currently have active research in these broad areas, ranging from computer vision to natural language processing, spatial journalism, 3D web technologies, media capture transmission, and misinformation and trust. Typically, we're looking for real world examples, and a lot of times we're trying to connect one of these big areas like natural language processing to a specific story or a specific capability for the Times. And our team in general very much errs on the side of applied aspects of these emerging technologies, with, of course, all the extra standards that come into place applying them inside of an organization like the New York Times. Typically, our process is, once we identify an opportunity or an interesting emerging technology, we dedicate a team to explore that space, to try and work on building a product or a capability in collaboration with other parts of our organization, keep iterating on it. And if we feel like there's a there, we sort of go all in and try to build it into a full-blown capability. And some examples on the next slides here of some of those other areas. First, when it comes to things like media capture, we are exploring the use of drones and how can we capture images and video and LiDAR data, and then not just capture it in interesting ways, but get it back to the newsroom more quickly so that those pieces of information can be turned around quickly. On the next slide, you see some of the various camera hardware that we've worked on. Everything from synchronizing cameras so that we can capture still images from different angles, all the way through to some of the work that we are doing, developing apps internally called Beam and Eclipse that allow us to use the cellular networks, especially the emerging cellular networks like 5G, and directly plug those into the high-end cameras that our photojournalists and videographers are using so that they can, as they're taking photos and videos, get those back to the newsroom to be put into our news report very quickly, which is a huge leap forward from the days of trying to find a Wi-Fi network at a Starbucks or juggling different memory cards. If your smartphone can automatically upload photos, we thought that high-end cameras and video should be able to do that with the much larger file sizes as well. An example in the next slide here is some screen grabs from some of the work that we've done with computer vision and thinking through how those techniques could help enhance our report. And so these are some examples specifically in the sports domain. We just published a video on our website yesterday that I encourage you to check out, which talks about how we used a computer vision technique to extract meter by meter speeds from the Summer Olympics in Tokyo this year, which is super interesting. And I encourage folks to take a look at that. Another quick example on the next slide is some of the tools that we built internally for our journalists. So in this case, we built an internal tool that helps align spatially thousands of photos and videos from the events on January 6th at the Capitol. Another example in the field of natural language processing on the next slide is launching a tool on our website that connects readers with trustworthy answers to questions on important topics such as the coronavirus or vaccines. So this is a tool that we launched that uses NLP techniques to cluster those questions together. So if a reader asks a question, even if they ask it in a novel way, we can connect them with a trusted answer from our journalists, which is super neat. And then finally, an example of some of the other work that we've done, and this is a personal passion project for me, is some of the work that we've been doing to stitch together both computer vision techniques and natural language processing techniques to generate human quality text transcriptions of millions of articles that go all the way back to the very first edition of the New York Times, which was in 1851. So we have, well over 10 million articles that are currently sort of stuck in just scanned images. And our team is working on a capability that will create digital native versions of all of those articles with proper headlines and bylines and properly segmented paragraphs, and even all the way down to little details, as you can see in this screenshot of things like M dashes. So this is just a quick example of some of the things that R&D is working on. But today we're going to go deep into one area specifically, which is spatial journalism. And so on the next slide, Lydia and Nick will begin to walk you through how we're on a journey as a team to create tools that allow our journalists to rapidly create spatial news assets and all of the design and technical hurdles that we have to work through as a team to try and bring that vision to life. So Lydia, take it away.
Thanks, Justin. Yeah, so that's a great introduction to this work and a little bit of a preview into how over the past several years, the New York Times newsroom has created these groundbreaking immersive experiences. Some of you might be familiar with recreating the Apollo 11 moon landing or using AR to visualize CDC guidelines for social distancing. So this initial work in the space has really demonstrated the journalistic potential of spatial computing. And as an R&D team, this year we've been further exploring this opportunity and trying to imagine what it could look like for the New York Times journalism to really push the boundaries of this medium by focusing in on the question, how can we help people understand the world by using spatial storytelling techniques? So Nick, if you could go to the next slide. This is really the question we want to focus on today. How can we help people understand the world with spatial journalism? And to expand on this, the goal of this work has been to discover how we can use the Times journalism as a contextual layer on top of the world, specifically using phone-based AR. So we'll be sharing with you some of the challenges that we've worked on, with that and sharing in particular from the design and the technical side, what repeatable patterns are needed to do so within a fast-paced 24-hour news cycle. So you might be looking at these two images and thinking, well, these look like the print version of the paper, and you are correct. This year, our team has worked on what we call news feature stories. And many of these stories have involved working with the newsroom to create augmented reality experiences that pair with a print or digital article. So this is an example of that. This was an article explaining how particles travel through and are trapped by masks. And we created an AR component to go along with this print. And there's also a web version that isn't shown here. But Nick, if you can go to the next slide, this shows the AR component that we made. On the right-hand side, you can see in this GIF an N95 mask that shows up in your space and then zooms you in into a microscopic scale where you can see and interact with the particles inside the fibers. And on the left-hand side is the Instagram story that went along with this effect on the Instagram platform where it was published. And so here it quickly becomes apparent in this example that there are different affordances that each of these mediums have, meaning that we can show slightly different aspects of a story using different technologies. Also, print is a technology too. So thinking about what can we show with print, what can we show with web, what can we show with AR? And our job has been not to simply translate patterns from one technology, so print or web, to the next, but really to find new ones working in this new medium. And that's what we've been working on this year. So on the next slide, this shows a quick overview of some of our work, which has ranged from rendering the movement of Olympic athletes, using motion capture, to Instagram selfie quizzes about CDC mask guidelines, to full-scale, explorable photogrammetry models of locations, such as this one shown here is a street in Chinatown in New York City, also done with a church in Harlem, and also ranging to visualizing scientific data, specifically here on the right-hand side. This is pollution data. On the next slide, our work also, it shows how our work has also involved creating interactable 3D products that you can place in your space for Wirecutter reviews. So that's on the next slide. Nick, if you can move. Got it. Okay, I don't know if there's like a delay or not. Thank you, it's perfect. So here we have the standing desk on the left-hand side, a grill you can open up, and a telescope. And then on the next slide, we have some preview of some AR games that we have created. On the left, a collaboration with the crossword. So this is called Shattered Crosswords, and you have to move this cloud of shattered words to the right alignment to find the word. And on the right, these are two versions of a game called Wire Loop, where the player traces a wire and heats it up and makes it glow to reveal a shape. So this is a really quick look at a variety of projects that we've worked on. We're happy to go into questions at the end on any of these, but we'll dive into detail on a few of them. But before we do that, I'd like to take a quick step back and go over some of the AR design concepts within these. On the next slide, here's an example of the further or a little bit more detail on this wire loop game that we developed. Here you can see Nia is playing on the right using her phone, and on the left you can see a screen recording of her screen. And I just want to point out some unique affordances of AR. Some of you might be familiar with these, some of you might not, but all these show up in all of our pieces in different ways. So I kind of wanted to ground us here before we move into the technical elements. So yeah, I just use the word affordance. So I wanted to define that. And we're talking about the affordances of AR. The definition I have in mind here is the definition from Don Norman in his book, Design of Everyday Things, where he says an affordance is the perceived and actual properties of a thing. So it's the fundamental properties that determine how a thing could possibly be used. And so to point some out here, we can see AR is inherently, like, one of its affordances is that it is spatial. So Nia immediately gets up to play. She's moving her body, she's moving her phone around, she's moving her hands. This also shows how it's interactive. She clicks to continue and she's moving her phone forward to light up the wire. AR, one of the affordances of it is that it's also non-linear. Here, there's only one wire to follow, but what happens along the way is determined by her. In this case, it's her score. And we could imagine, a case where there's a branching wire. And these two elements in particular, the interactive affordance and the nonlinear nature of AR, really break the traditional, or is an opportunity to break the teller-listener paradigm. When we think about like reading an article from top to bottom, it's a very linear experience. And here, the user or the reader, player now has agency. We can also see that AR is a very immersive medium. If we look at the recording of her screen, the world she's seeing through her phone darkens a bit to focus on the glowing ring. And this is a very light immersion, but we could definitely imagine bigger effects. This kind of like immersion of the darkening of the screen plus the wire on top of the space she's in is this additive layer that creates new ways of interacting with the news in your space. So that's the kind of additive layer affordance. And finally, in terms of scale, the scale doesn't change a lot here, but we could imagine what would this game be? How would this game be different if she had to play it on that small chessboard that she starts at? Or how would it be different if she had to walk the whole length of the park to play it? So hopefully this can start to give you some ideas of the like design and interaction challenges that we've been working on. I think that all these affordances and these opportunities are very exciting elements to design with. But like any emerging technology, it also comes with unique constraints. So the software that we use to make these effects is called Spark AR, and that is the software that's used to publish augmented reality, to make and publish augmented reality effects on the Instagram platform. It's kind of similar to a game engine, like a light version of Unity, if you ever use that software. Some of the particular constraints of this software is that the effects that are uploaded to Instagram have to be 4 megabytes or under. Instagram used to have a policy that we couldn't add any screen space UI. They recently updated that, but in our past effects, you'll notice that. It also doesn't have any haptics or any type of like computer vision to be able to identify objects in your space. So this is kind of the flip side of working with emerging technology. And I think Nick will get a lot more into this, that there are constraints that may not exist elsewhere, or that once a technology has become mainstream. But I think that creates a lot of really great opportunities for creative innovation. And I was talking about how exciting all these affordances of AR are, but they also provide challenges as well, because these new capabilities like immersion and interactivity, many people are unfamiliar with them. And so they don't have an intuition of how this technology works. And I guess when I say intuition, I think I really mean familiarity, because we are all familiar with the web and print. And so the question becomes, how do we guide our users, our readers through these experiences? And this is part of our job that I'd like to touch on next and give a bit of a preview to a couple of these specific projects or specific AR effects before Nick goes into more technical detail on them. So on the next slide, we have the AR effect that we called reopening. The goal here was to take users' inside data, specifically data from that was visualizing airflow within a classroom. So the question of guiding users is particularly important, because on these projects, we are working with the newsroom to take a long or complicated story or concept and deliver it in a new format in a digestible way. So the next slide shows a preview of this effect. And you can see how there's a classroom on the left-hand side, and we worked with the newsroom to render an airflow simulation in the classroom and bring it into augmented reality. And here we really need it to be accurate and for all the necessary context to be available and clear to the reader. So you can see here there's a student in the front of the classroom who has COVID, and this is simulating if there were a student in this position with COVID. It's playing out how the air with the contaminant would flow around the classroom if the window were closed versus if the window were open. And then the extra augmented reality component that we added was on the right-hand side here, with the second half of the experience allowing the user to go inside the classroom and walk around inside of this data. So again, thinking about our affordances, this being immersive, spatial, interactive, nonlinear, being able to adjust the scale and create an additive layer. The next slide shows how we have used a few of these affordances here. In the classroom simulation, we have separate chapters or tabs which allow the reader to toggle back and forth between them. So instead of like a really strict linear experience, they are able to explore a little bit with guides attached. We also have this dynamic scale bar during the immersive classroom section that follows the camera, so that anywhere they look, they have the necessary context that they need to be able to understand the data that they're looking at. And the scale bar moves as the reader or the user walks around, allowing this to become a very immersive and interactive experience. Another project that I wanted to touch on quickly was the Dixie Fire project. This was, I guess, had the formal title of Wildfire Storms. The idea here was, or the challenge was, how can we spatialize large scale data in a user's space? So for this piece, we created a model terrain, a terrain with a cloud model that users could place in their space. On the next slide, there's a preview of it. And this model shows how the Dixie wildfire cloud reached different parts of the atmosphere. And Nick will go more into how the cloud is made, but again, here, the context of this piece is really important. How do we clearly show the atmosphere in a way that might be different than you could achieve in print or on the web? So on the next slide, to point out some of these affordances we worked with, you can see here that this is a very large scale piece of terrain that we're still able to put in your space, and the user can use a panning motion to see it from different angles, to be able to explore it on their own while clicking through to see more additional information on the different parts of the atmosphere that the cloud reached as it developed. Here, the interaction was a little bit more linear because the user wanted to tell wanted the information to come in a specific order. So we had the tap to advance function, which kind of mimics scroll on the web. So that was a very quick overview of some of these, and Nick will go further into them. But wanted to kind of ground this next part you're going to see with some of these design principles, so you can think about, keep in mind how we're working with these different affordances of the medium.
Great. Yeah, thanks, Lydia. So as Lydia said, I'm going to talk to you a little bit more in depth about some of the technical challenges that we faced in making these. So I'm going to cover just two of the effects. I'm going to start with the NYC school reopening effect. And for this, the technical challenge here was mainly visualizing the spread of airborne virus using fluid simulation data, which is very big, but doing that in under 4 megabytes, which is quite small. And this is the way we did that. So the data came from health experts and building systems engineers that we worked with, who simulated the spread of COVID through a New York City classroom. So we received data for 2 simulations, one with the classroom's windows closed, another with one window open. The resolution of each simulation was around 100,000 points, sampled somewhat irregularly within a volume, around 122 times over 15 minutes. Lots of data, 25 gigabytes of data that we needed to somehow fit into Spark's limit of 4 megabytes. So the data came to us as a ParaView project. If you're not familiar with ParaView, it is a data visualization software. It doesn't typically do simulation. Simulations are done elsewhere, and then the data is imported into ParaView and visualized and analyzed. You might be familiar with analysis of aerodynamics of airplanes or race cars and the way that it simulates airflow and air pressure over those. That's usually done in something like ParaView. So the main image here that you can see is all of the raw data. And the first thing you might notice is that it very quickly obscures the entire classroom as soon as you let it play through. So in legibly visualizing this data, the first thing we have to do is select which data we're going to visualize, which both makes it clearer, but it also saves us on some space because we're going to be removing or hiding some of the data. A couple of ways you could do that would be on the right top, selecting a threshold of say 5 parts per million and only displaying parts that are going above that threshold. So that gives you what's called an isosurface. That's sort of that inflating balloon of contaminant above the infected student. Another familiar one might be a cross section where you are just visualizing the data on a 2-dimensional plane arranged vertically in the classroom on that bottom right image. But we used a pretty unique form of visualization called stream tracers. And the way these work is you start, say, with some spots around the infected student's mouth, and you draw a line through the volume following the direction of airflow and coloring as you go based on the concentration level that you sample. And so they all go in different directions because it's a chaotic airflow in the room. And the benefit of this is that it both visualizes the airflow direction, which isn't so clear in the previous visualizations in the previous slides. And it also simultaneously visualizes the concentration level in the form of color. So we thought this was just really clearly illustrating what was going on in this room. And by selecting a subset of the data in this way, it both becomes clearer and also decreases the size of the overall data. The last thing to take note here before we go on is that the air pattern in this room is stable, like almost like an eddy in a river that stays the same shape even though new water flows through it. So we're actually able to just take one airflow model and animate only the color. So that saves us some space too. So out of ParaView, we then enter Blender and use its ability to be automated with Python. As I said, we use one static model for each of the scenarios. You can see those on the top right. The very top is the window closed scenario, and the sort of middle right is the window open scenario. And these models were decimated in Blender, and they shared a very special texture that you can see on the bottom right, that red and green image, which will be explained later. And it was generated with this like automated Python scripting in Blender. We did all this automation using our Dockerized headless version of Blender and our custom Python scripts. That version of Blender, you can actually, it's open source. The Docker files are open source on the GitHub link shown there if you ever need headless Blender to do some automation for you. So I'm going to talk a little bit about what this mess of color is. This is the data from those two scenarios encoded into color channels. So the red channel is the window closed data and the green channel is window open data. Some of you may find this quite familiar because this is an old technique for doing 3D graphics before some of the newer advances in 3D graphics. This was common in web graphics, encoding data into color. What I've found is that when you work with really new technology, often you find yourself hitting the same constraints that you outgrew in previous technologies. So often reaching back to older techniques are a way to get a little bit further with the cutting edge technology of today. So I'll explain what this technique is doing in this case. So the brightness of the red, and we're just going to focus on the red for now. This is a window closed scenario. The brightness of the red color represents the concentration of airborne contaminant. And so what happens is the shader that renders the streamlines in the room reads redness and uses that to look up the final color from a color ramp. So the red color is really just a proxy that later, using a lookup, becomes the color rendered to screen. And then each streamline each stream tracer, each spaghetti strand, let's call it, is assigned a row of pixels. So here we're looking at a blown up row of pixels that show the concentration level along that stream tracer. So you can see the left side is very high in concentration. That's probably where the stream tracer began, by the student's mouth, where it was exhaled. And then the right side is much lower in concentration. That's towards the other end of the stream tracer, somewhere else in the room. If you take all of the stream tracers, all the data from the stream tracers, and stack those rows on top of one another, you get this big stack. This is the entire room full of stream tracers encoded into this column of pixels. So each row is a stream tracer, and the entire thing as a set represents the state of the classroom at any one moment in time. And lastly, we use 8 stacks, 8 frames of animation that we cycle through in the final animation. We use 8 frames. That would be really kind of a jerky animation, but we are able to interpolate between neighboring stacks to insert more frames than we've got. And the reason we're able to do that is because there are no sudden changes in the data. It is all a gradual dispersal. So interpolation, it remains faithful to the original animation, even though the original data had 122 temporal samples and we've reduced it to 8, they're indistinguishable when you see them side by side. So what we've ended up with is 2 different models, each about a meg, and this special color texture, about 200K, and we've hit our mark of under 4 megabytes by quite a bit. And so, this is the final rendered product. We were able to get these 2 scenarios that we could compare for a really low amount of space and remain faithful to the representation of the data. And then the next and last one that I'm going to talk about is the Dixie wildfire. In this one, of course, we face the same challenges of the size, but we also wanted to display volumetric cloudy data without modern volumetric rendering. So without things like ray marching that you might use on other platforms, we needed to have a clever trick to display these clouds in AR. So I'll start with the data. So Neil LaRue, who's an atmospheric scientist who studies wildfires, popularized this technique for creating 3D animations of wildfire plumes from radar data. That's what you're seeing on the top there. That's his work. We decided to work with him and take that technique further for an interactive web article. The animation of the web article is on the bottom there. That's what published online. You'll see there's a lot of data goes into this, the fire footprint, the shape of the clouds, even lightning strikes that are caused by clouds created by the fire. It's a really interesting mess of weather that you should see the original article to learn more about. And then that was the article. Then we took one moment from the article's animation and visualized it in augmented reality. We took the highest point in one of the highest points in the plume's life and analyzed how far that reached in the atmosphere. So the data, as I said, is radar data. We used, they're all across the country. We used 3 radar stations in California and Nevada that picked up the Dixie wildfire's plumes. These observations are made every 10 minutes. So you can see a little animation of that on the bottom. That is the plume of the Dixie wildfire churning there, getting picked up by radar stations. If you're not really familiar with radar, it helps to understand it to get a sense of what the shape of this data is before it enters our pipeline. Radar stations beam out pulses of radio waves and then observe what gets reflected back. And then denser stuff in the air, like raindrops or large ash particles, reflect the radar pulse more powerfully. So the more powerfully the reflection, the higher the reflectivity measure in the bottom graphic there, higher on that scale. So the power of the reflection maps onto the color in that data. And then the distance from the station is determined by the timing of the reflection's return. So it faces in one direction, it sends some pulses out, gets them back, and then turns a little bit and keeps doing that until it sweeps all the way around in a circle, painting the picture that you see at the bottom there. That's just one sweep. Each sweep of the radar aims at a higher and higher angle, which results in a kind of stack of these slanted observations that you see in this animation. This is in polar coordinates, so it's not great for computer graphics software. We need to take this and we need to conform it to a regular grid, to Cartesian coordinates, and interpolate to fill the gaps in this data so that we can get a more familiar representation of the shape of the wildfire plume. We do that, we do all of this in Python first. So we did all this data gathering and interpolation and conversion in Jupyter notebooks. Really skipping over a lot here, but if you look at the right side, the 4 images there, the top left is color imagery of the surface that's pulled from the Sentinel-2 satellites. The top right is elevation data encoded as brightness that we got from 3DEP. The little magenta dot there is lightning strike markers from Vaisala. These were not, this is the only data that wasn't used directly. We actually passed that off to CG artists that added in the lightning strikes where we placed these dots. And then finally, we used a Python library called PyArt, which is dedicated to visualizing radar data to convert those slices of radar data into 3D volumes that we then visualized in Houdini in the next step. The format we used to get into Houdini was OpenVDB. There's another Python library that allows you to write those files out. So we assembled these frames of animation as VDV files and got into Houdini. I'm going to skip a lot of what went into the visuals for the article. The top image here is one step in that set of activities. You'll notice it's pretty detailed. We add back in a little bit of cloud noise in order to give the surface enough texture to pick up light and actually be legible. Again, increasing legibility without sacrificing accuracy. These decisions are always made hand in hand with consulting scientists. So starting with that though, starting with that as a VDB, we can't just take those VDBs and then show them in AR. The platform that we use doesn't support this sort of thing yet. So we use a process similar to medical CT scanning, where in Houdini, we take 100 cross sections of this plume, and then we export those as those slices as textures. This was actually a technique that we found online by this person, Marius Ader. If you're curious, you can go check that out on that YouTube link. But this is the result. So we get a bunch of slices of the cloud. You see that in the top left. And we get we place those on a model that just consists of a stack of squares. And when you stack those images up, what you get is what you see on the right, which is a pretty convincing volumetric cloud in your space on a platform that does not support volumetric rendering natively. Those are the 2 deep dives. I wanted to say one last thing. I mentioned it a couple times, but it's really, really important to us that every time we do anything with the data, we're very clear about it to ourselves. We document it for our readers, and we do it with the help of scientists to confirm that we are still faithfully representing the data. Just to show, so there's a lot goes into this. We do a lot of work, make a lot of renders just to double check ourselves. So just to take a couple of examples from this project, on the left, we chose a sequence of the Dixie Fire that happened to be picked up by a time-lapse camera in real life. So we were able to place a virtual camera in Houdini and compare our renders with the actual footage and make sure that we were representing it faithfully. And then on the right, we also made this sort of like nested isosurface render to make sure that the interior maintained its integrity. We never even showed the interior, but we thought it was important just to double check that all of this data was making it through our pipeline, and it was really preserving the integrity of the data, even in the interior, even though we didn't show it. So we really take it seriously. We really ask and question ourselves a lot. And at every one of these moments, we have a scientist nearby to say, you know, do you have any red flags? Have we faithfully represented this? So that is it for me. I'm going to turn it back to Justin to wrap us up.
Thanks, Nick and Lydia. I want to make sure we get to questions. I'm going to very quickly run through the next several slides here. But the main point on the next slide is that across the broad interest areas for R&D, we have specific types of research that we're interested in as a team. And so I'm not going to speak to all of these. They're on our website. But if you're interested in working on all of them, any of them, I encourage you to reach out to us. We have internships, we have fellowships, we have job openings on our team. And as you can see from the deep dive today and some of the earlier work that I was speaking to, our team gets to work on several pretty neat projects with some really cool impact. But as you can see, these are some of the problems that we're interested in on misinformation. On the next slide, you can see some of the problems that we're working on with 3D web. In particular, you may have seen some of the stories that use environmental photogrammetry models that are rendered within an article page. That's some of the type of work that we're doing. The next slide hits on some of the other spatial problems. The next slide is talking about some of the media capture and transmission areas that we're interested in. The next couple slides speak to computer vision and then NLP problems. And all of this can be found on our website, which is rd.nytimes.com, which is on the next slide. And with that, I think I want to get to questions. So we'll go right into that.
Thank you. Thank you to the three of you. That was amazing. If you could stop sharing screen, because we'll let you take a 1 minute break while we go with some questions for our opener speaker, and then we'll get on. We'll do sort of the opposite of your from high level to technical. We'll start with some very technical questions and then get to some more high level ones. So Keunhong, hopefully you're still here. We have some questions for you from the chat that we've received. So I'll just jump to the first one. I'm reading from the YouTube chat. I noticed that the numbers on the coffee machine in the HyperNeRF interpolated viewpoints are very choppy. Is this a result of there not being a smooth transformation in the lifted coordinates? How do you deal with transitions that are not continuous or smooth in any lifted dimension?
Yeah, so that's a good question. I mean, so we actually have no guarantees for interpolating things, right? I mean, we treat all the frames as kind of a bag of observations. And kind of the coffee thing was kind of it was a pleasant surprise that it worked, because we're doing multi-view reconstruction. And for that example, we only have like one observation, and the scene is constantly changing and you're moving the camera along with it. So there's no multi-view consistency per state. So there's no guarantee that the reconstruction is going to be consistent. So that's why the numbers, I think, look a bit weird, because they're switching really fast, and the numbers, they don't, like, the appearance doesn't change smoothly. Like when it goes from like 1 to a 2, there's no smooth transition between those. So I think that's why it's choppy.
Okay, yeah, that makes sense. Another question that I had from, maybe because I'm a geometry person, you told us about how having this like planes wasn't doing good enough for the interpolation, so you sort of use this bent slicing planes. And I have to wonder, are these, I guess I'll no longer call them planes, I'll call them slicing surfaces. Are they geometrically interesting in any way? Do they minimize something? It reminded me of some works of minimal surfaces. I don't know if it's something like that. Have you looked at them? What do they look like geometrically?
Yeah, so we try to keep them really smooth. So there's actually a knob, like the number of frequencies and the position code. It controls, like, it goes from kind of like a sort of a bendy sheet to crazy mountainous, like needle-like structures. And I tried to keep it as smooth as possible. So they're not that interesting. So kind of, I mean, it's hard to visualize because the ones we use for the 3D scenes are higher dimensional. But if you look at the 2D examples, they're kind of like, they're kind of like the like gum wrapper kind of.
Okay.
Kind of look like that. Yeah.
I'd love to know what specific properties it has in higher dimensions, because, like, you know, something can look simple in 2D, but later be harmonic, or later be, you know, biharmonic in other dimensions. So I think that's very, very interesting. Okay, so I'll move on with a technical questions for our headliner speakers. I believe I would address this to Nick, but if any of you wants to jump in, we've never had a 3-person headliner, so we're making it up as we go. So in this simulation, in the classroom COVID simulation that you showed, you're only storing the data that you already got from like someone who did the simulation for you, right? So this 4 megabytes is only for the display of this data, so to speak. Then I was wondering, because like the extremely cool version of this project would be that I tell you what my scene looks like. So I tell you, hey, I'm in a room, my husband's like 2 meters away from me, and then I got a visitor that sits over there. How risky is that? Am I gonna get? I tell you something like that, and I tell you like where the windows are and if they're open, and then you tell me how risky that would be. Like that certainly has like a very good public interest and service, right? So, but then you would have to store the animation software itself, right? So I wonder if that's something you've considered, and what would be the main challenges to go all the way?
Yeah, I mean, that's an excellent idea. The main challenges there is just that this kind of simulation is extremely expensive, computationally to perform. So I don't know, the specs of the computers that were used to generate what we used, but like I said, the resolution as far as sample points in the room, 800K, and that is taking into account a lot of factors. It's the movement of all the particles, it's the interaction of heat in the room, it's taking into account the heat of the breath of the students as they breathe out. That's why the contaminant drifts upward. Even the heat of laptops in the room was accounted for. Wow. As well as airflow coming in from the window and seeping out through cracks underneath the door. All of that needs to be specified and calculated every frame. So there's no real-time version of what we received from the scientists that ran these simulations. You could imagine a sort of simplified version of that could run on some systems, but then again, we're talking about mobile and we're talking about on the Spark platform, which was not made for that level of simulation. I think we're a ways off before we could tackle something like that, but I love that idea. So that's something that I hope we will be able to consider someday.
I like that because we work in computer graphics, and sometimes the main application of computer graphics that we pitch is like animation and video games, and you can see smoke coming up in video games. We have fluid simulations that run in real time, right? So maybe it's a matter of balancing, right? When smoke goes the wrong way in a video game, maybe it looks unrealistic. If COVID particles go the wrong way, you got a lawsuit, I guess. So like it's probably you have to manage a few more variables than us.
I will throw out one other interesting challenge, which is this needs to be defensible. So you can make a fluid simulation that looks realistic, but if you can't, but we have the added hurdle of it needing to be scientifically defensible. So every single decision that the scientists needed to make about the heat and how much contaminant is coming out of an infected student, each and every one of those needs to be defensible. And so it just adds a little bit more complexity and care and to the equation, beyond just what would be simulated in a game engine.
Okay, makes sense. I'm just going to move into the next question so that we get to all of them or most of them. There's a question that came up during Nick's section of the talk, but it's sort of philosophical. So, whoever wants to answer can answer. I'm just going to read it. These visualizations are extremely compelling. I was wondering about the journalist's efforts required in person hours versus the duration of the reader's engagement. So is this quantity, I take it, going to be similar to, for example, a print article? How long does it take to write, I assume, edit and publish an article versus the time that it takes to read it to the reader? More broadly, how does one measure impact from a newspaper standpoint? I realize it's a massive question, but if you could keep it under a few minutes, because we're going to get to the rest. I realize we could talk for an hour about this.
I'll say briefly, both of the projects that I outlined were months long, wow. And probably even more than that when you take into account the work that happened before I was involved, before there was any engineering need. So that's not always the case for our AR effects. But definitely a lot of time, especially when it comes to something like these complicated stories, a lot of time goes into it, especially when you compare to how long it takes to read an article, or even more so when you compare it to how long it takes to interact with an AR effect, which is usually, a minute or a few. But anyone else want to jump in?
Well, the other thing that I would just add is I think that's sort of philosophically at a high level is what the New York Times does best, right? That's why people who are subscribers help the Times, because you have conversations with scientists, you have engineers, you have people who are investing months of their lives into a story. These are visual stories. There are people that do that just on investigations, visual investigations all across the Times. You have these teams of people who are really going deep on these topics, and I think that's why it's fun to work at an organization like the New York Times, where this level of investment goes into an individual article. And you're right that most people seeing that visualization, if they saw it on Instagram or in an article, probably didn't realize how much effort went into bringing that to life. But it's pretty fun to work on.
That's a good point. But, just to be completely clear, that addresses like one part of the quotient, which is how much work it goes into it. There are other. When you were talking, I was thinking of the January 6th visual investigation video, which I didn't know you were involved in. Your team was involved in, and I don't know if I've seen a piece of media that so many people near me have watched many times. Like when I read an article, it might take me like a minute of skimming it, but that video I was like glued for 30 minutes several times. So like there's certainly like the other part of the quotient, the engagement is also much higher. So maybe it is worth it. I don't know.
Yeah, I mean, I think that's a good point. The different types of pieces that the Times publish are meant to be engaged with in different ways. Some articles are meant to be a quick read, some are a much deeper dive, and like the videos, some are much longer and meant to be sat with like that. I think with augmented reality experiences, we do try to keep them relatively short, just because it's hard to hold your phone up for like 30 minutes, say,
right.
Looking through
That
it.
makes sense.
So kind of more for that reason, and that's why usually if it's an experience like this where it's the wildfires or the classroom simulation, where we've designed it in AR to be this, maybe like 5-minute experience. It usually, when it's complicated like that, usually is paired with a print article or web article where we know people can more easily spend more time with it. So that does come into consideration, and something that that we think about. But I guess that's an interesting idea to compare like time spent with AR versus print versus I think that's a good question.
Yeah, definitely. I just have so many questions. I'm going to get to them, but I would respond with another question, but I don't have the time. So let me ask this question, because Justin brought up the Times Machine thing, which, by the way, if you are listening to this and you haven't been to the Times, like New York Times Time Machine, you can spend days just going through old newspapers. It's amazing. The first one is like, the Lincoln assassination. So there's like a lot of time that's covered. I discovered it one day and I lost like a whole week of work. Don't tell my advisor. So anyway, but that example that you brought is very important. And it raises a different question, which is that if you look at the newspaper if you look at the Lincoln assassination and the Kennedy assassination, they're basically the same newspaper cover, right? They're the same product, they're the same format, they're the same words, basically the same language. It's very easy to archive those two together, right? However, if we move on, some would say if we move on to telling stories using the technologies of the day, so for example, we tell a story in Snapchat or Instagram or using the New York Times app, it's harder to maintain this paper of record archival property that the New York Times has and we all enjoy by looking at the New York Times Machine. It's going to be much harder to digitize that one application that only ran in that version of Instagram from 50 years ago, if for the people looking at the pandemic in 2070. So how is that addressed, and do you think about this?
Definitely archiving content on platform is a big priority. There's an entire team of taxonomists and archivists and all that who work on this problem. And I agree that as technology evolves and there are more mediums and more off-platform ways for people to interact with content, there is an interesting challenge to that. Certainly on platform, we work on that. Perhaps Nick has some ideas about where that's going, but it's totally a legitimate and interesting question to capture all of that and make sure that it's recorded. I know that there are some interesting problems off of the Times website where, you know, when you link out to things, that I think there was some publication did a study recently where they showed news organizations linking out to websites that no longer exist. And so that's another big challenge of what happens once websites that were part of news stories don't exist as well. So it's a big challenge, I think, in general for all of us who do things that end up on the internet and different software platforms. But great question.
Yeah, great answer. Yeah, I guess the problem is bigger than, yeah, I guess the moment you start doing journalism online and just having links, that already is a problem. So that's a good point. So I want to end with a question that I actually want to ask all of you here. So both the headliner speakers, but also our opener speaker, Keunhong. There's all these algorithms that work on, you know, new viewpoint rendering. So, you know, like Keunhong's algorithm works on, it takes some images or some piece of video's input and it renders another part of the video. So if we're doing the January 6th video, we could look at one part of the Capitol and, or like one part of those like weird, surprisingly many streams that people, live streams that people were doing while they committed criminal things, and move it around and look at other angles of the video, right? Completely new angles. And I'm, by, you know, watching Keunhong's presentation and then watching your presentation, I'm wondering, where is the truth? Like, because like I know that Nick said no scientists were harmed doing this. As a scientist, and I talk to other scientists, I wouldn't take scientists' word that, you know, as gospel. Like I would, it doesn't reassure me as much as maybe it should, because many scientists do very unethical things, and you know, you might move the phone around, it may render a person that wasn't actually there, or things like that. So how does that affect? So I guess I want to ask Keunhong first, if this is like an ethical concern that you've considered working on this work.
Yeah, so for the NYT line of work, I think it's a little bit less of a concern because kind of so it's multi-view reconstructions. So we're not trying to hallucinate anything that wasn't there or kind of replay. I think it gets a little bit murkier if you try to like replay it back in a certain order, or you start trying to drive the face in and kind of make faces that you weren't making before. Or saying things that you weren't. I think that gets a little bit trickier. Yeah, I mean, it's a problem. I don't have a good answer.
Well, but when you have many views, you'll have occlusions, for example, and your algorithm will fill out those occlusions with some interference, some prior, things like that. So it is hallucinating to some extent, right?
Right. So if you're on the left side of your face, you're right, like, and you render the right side of your face, it'll render something. You'll probably just keep it fixed in like maybe the kind of the average position that it was when it was captured.
Yeah, I guess I'm thinking if it renders the right side of my face, you know, and say we're using this because, you know, there's some video that's like newsworthy because someone got caught in a criminal act, right? And you're rendering the face. What is the duty in the researchers or like in the product to show that, you know, maybe that face is coming from the training set? If you know someone with that face, then go and report them to the police, because that might come from the training set. It may not come from, you know, the real image that was taken at that point. So I guess I'm asking about the broader line of like NERF-based works.
Yeah, I mean, I think research, I guess we should provide the tools to make it easy to kind of just like know when something's novel and not like an accurate portrayal of what during capture time. So maybe give it a way to like, maybe you want to like render it in a different color if it was like an unseen view, so that people know that it's something new and not like something taken at capture time. But then, I mean, it's not a fine line, right? Because like when you take a picture with your iPhone, like there's a lot of processing that goes on, and you could argue that like the final picture you get isn't this like the actual sensor data. But then, like, I don't know where to draw that line.
That's a good point. Okay, so let's pass the ball to the New York Times people. Then we as researchers, let's assume everyone is just as very well ethically informed and committed as Keunhong here, and sees as part of their part of the duty to transmit which parts of an image are interpolated, which parts are not. But there's this fine line between what is acceptable image processing and what is inference, and when is inference truth that can be put up in like a newspaper, the front page of a newspaper. Once the researcher has told you that, what is the duty of sort of the intermediates that you are, and how should this be transmitted to the public?
Yeah, I think the general answer is that some of the same techniques that the Times has used for decades come into play. So we have teams of editors. We have people that it's their job to understand not just what we're saying, but what we're not saying, just analyze issues from every angle and really have complete literacy of a story. The same is true of any technology that we use and introduce. They need to have complete literacy of what the technology is and is doing. And from my personal experience, I spent a lot of those months that I mentioned in conversations explaining to non-technical editors exactly what each step of my work was doing, because we could not sign off on the story without all of those people understanding what was being done and understanding whether that was defensible, as I said, or anything like that. So I don't think that there's always new technology. Even photographs are a technology that can be abused, and any number of things you can dream up for the future. I think just the principles that the Times is founded on, that's a big part of what this is, being very deliberate, taking the time. If we don't understand, we wait until we understand it. Those sorts of things I think are really important.
Just to build on that, as Nick was demonstrating in some of his slides, they're in addition to having a standards desk at the Times and editors and researchers and fact checkers and a process for corrections and all this stuff that's really been with the media organization that has existed since 1851. There is this effort to validate all of the data in multiple different ways. And so as he was showing, validating the radar data and correlating that with actual photos and videos of the scene to make sure that they are showing the same thing. And we try to do that in a lot of different ways. And then in some of the other things, like the classroom example, really trying to over communicate in an article piece, for instance, where that data came from, who was the person that ran the simulations or the organization that ran that, how can you read more about that? And you can find that a lot at sort of the end of articles. There'll be sort of an oversharing of information about where that underlying data set came from, so that people can sort of go off on their own and try to assess those things on their own. And then if for some reason there was something there is a process for reaching out and communicating that, and an entire team of people who are dedicated to making sure that those things are there. And if there's a correction ever to be made about something, then there's an entire process that has existed for a very long time to do that. And so that's one of the fun things of working on these problems inside of a media organization, because there is such a high bar with these new technologies versus just sort of turning something on and doing it and deploying it it's tough for us to do.
The process is a little bit more complicated than our analogous, which is we just tweet an image and say, hey, look what I made. I had the feeling that Lydia wanted to.
Oh, I think I don't have too much more to add. I think that this is a really important almost, existential question. This has been debated in so many fields. And I think what you actually just said, process, is a really important word. The part of the Times mission is to seek the truth. And that is a process that, Nick and Justin just described. And there's always, we always publish the sources and how we made all the simulations and all those qualifications of each data set and how it was used, because we do take this seriously. And I think there's been so many cases where we're not the editors, but we work with editors like Nick described, and they are, if there's any uncertainty, they either want that explained or they'll say we're not ready to publish. And so, just to add a few more details onto that, I think it's an ongoing process and question that I think it's a great one.
One final note on this topic is just bringing it back to the R&D team specifically on the issue of trust and misinformation. That is a whole area of research that we are interested in. And so you can check out our website. We have active projects thinking about some of the challenges of media provenance on the web today, and what is the role of media organizations like the Times in helping make the web a healthier, more trustworthy place, and what are some of the technologies that we can contribute to as an organization to help make the information that people consume more trustworthy, and how can we take some of the techniques that have been in media organizations like I was just describing and try and bring those to the technology world, especially as that's getting into murkier territory, per your point of some of the capabilities that are evolving.
Yeah, thank you. I think that was a very thoughtful answer. I would stay with you for 2 more hours, but we have to end at some point, so let's leave it here. To use New York Times jargon, here's what else you need to know today. This is the last session of the year and the last session of the season. So I want to wish you all very, very happy holidays if you celebrate. And I would also like to thank my 2 co-hosts, Derek and Ottman, and also our advisor, Professor Alec Jacobson. Without them, all of this literally wouldn't be possible. I also want to thank all the artists who design amazing posters for this year's sessions. And of course, all our speakers who are really the ones to thank for the success any success that this colloquium had. It's up to the speakers. But most importantly, I'd like to thank you all for coming and watching our videos and making this last year, at least for me personally, much more bearable. Have a happy and safe 2022.